All right then, looks like we're live. The audio is fine, the video is fine. Okay, I'll just wait for a couple of minutes and see if someone comes online and then I'll begin. All right, let's just begin. So, in the previous lecture, we discussed, I introduced you the idea of eigenvectors and eigenvalues, and we didn't really do many computations. We just saw a few examples where it was easy to see what the eigenvalues and eigenvectors were. And this idea of viewing matrix multiplication as transformations of the space, particularly in the two-dimensional or the three-dimensional case, where we saw that some matrices might rotate your space, some matrices might flip your space, some matrices might be projection matrices, which will make your three-dimensional space into a two-dimensional space, which is to say that the way it makes it into a two-dimensional space is if you give it all the vectors in these three dimensions, it will give out vectors only in these two dimensions, right? There will be no result of this matrix multiplication that is outside this plane. And we saw that we introduced the eigenvalue problem, the eigenvector problem, really, that what are vectors that under matrix multiplication, under these linear transformations, stay in the same line that they originally were, right? So they only get scaled, but they don't move out from their original space, sort of, right? The original subspace, their line that they were in, right? So those are eigenvectors. And we saw in different cases how we can immediately see what the eigenvectors are. And so this really was the main problem, right? So find x's such that when you multiply a with an x, it gives you the same vector just multiplied by a lambda, that is just scaling. So matrix multiplication is the same as just scaling the vector, right? And that's the equation that we're going to solve today. So we're going to learn today how to solve this equation in the general case. So the question today is, how do we solve ax is equals to lambda x, right? That's the question that we're going to address today. Okay, and so let's see what we can do here. So on the left-hand side, you have, let's say, an n by n matrix being multiplied by an n by 1 vector. And over here, you just have an n by 1 vector being multiplied by just a number, right? It's just a scalar number, right? So the product on both sides is really a scalar, right? Sorry, not a scalar, it's just a vector, right? So the result of this is an n by 1 vector, and the result of this multiplication is just n by 1. So on both sides of the equation, you just have vectors, n-dimensional vectors, right? Okay, so I'm going to do something. We're going to try to bring this lambda x on the other side, and so the way we're going to do this is we're going to subtract lambda x from both sides. We have to be careful when we're doing algebra on matrix equations. It's very similar to algebra that we do on real numbers, but there are some subtle differences. So ax minus lambda x, and on the right hand side we have lambda x minus lambda x. So this is a vector subtracting the same vector. This is going to give me the zero vector, right? So this is the zero vector. On the left hand side, this is a matrix times the vector being and this one is just a number times a vector. At this point, we're tempted to say that as an algebra equation, I can see that this x appears in both the terms, right? So this is the same vector being multiplied by a matrix, and over here it's the same vector being multiplied by a number. So usually what we do in algebra is when we have such a situation, we take something common, right? So the way we can do this, maybe in algebra we can write x times a minus lambda, right? But this equation doesn't really make sense, and so this is really I did this step, but this is the wrong step to do, and it's important for you to understand why this was not the right way to proceed. The reason this is wrong is notice that this vector is an n by 1 vector, and this matrix is an n by n matrix, and this is just a number. So first question is, how do we really subtract a number from a matrix? And the second question is, even if we somehow manage to do that, that's not possible. How are we going to multiply this vector, which is n by 1, with whatever comes out? Is it a matrix? Is it a number? What's happening here, right? So this is not the right way to solve this problem. So I'm going to erase this and write the right way. So is equals to 0. Now we have to keep the order correct. So x was on the right hand side of this matrix, right? The way to do this multiplication would be to put it on the right hand side. So I can write this. Let's just leave it like this. But I want to convert this term lambda times x into, this is a number right now. How can I introduce a matrix here without really changing this term, right? So for example, consider the following. Let's say I have the vector x, 1, 2, 3, and I'm multiplying it with lambda, then that becomes lambda, 2 lambda, and 3 lambda, right? What if I did something different? What if instead of this lambda, I wrote lambda times the 3 by 3 identity matrix? So this is I, this is 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? Okay, so the result would be that first this matrix gets multiplied by this lambda. So I can write lambda 0, 0, 0, lambda 0, 0, 0, lambda. And then when I multiply it with the vector 1, 2, 3, I get, again, so over here I get lambda times 1, then 0, 0, which is just lambda, then 0 times 1, lambda times 2, so 2 lambda, and 3 lambda. So really what we did was introducing, again, you can think of it in simple terms that introducing the identity matrix doesn't really change anything. So lambda x can be correctly written as lambda ix, and we're just introducing this, so this now becomes a matrix, right? So I'm going to rewrite this term as minus lambda identity x. And the reason I've done this so that I have matrices on both sides of on both the terms. Okay. So now we're allowed to put the matrices in parentheses, and so I can write a minus lambda I times x is equals to 0. So now this equation does make sense because this is an n by n matrix. This identity matrix is an n by n identity, and this is just a number. So the result of these two being multiplied would be a matrix, the result of this. So n by n matrix, you can do a subtraction of n by n matrix from an n by n matrix, right? And you can then multiply it by an n by 1 vector to give you this n by 1 0 vector. So this equation does make sense now. It's a perfectly valid equation. Okay. So we've rewritten the equation into this form. And now, if you notice, and this is just a matrix, I can maybe call it A star x is equals to 0. And this now is a very familiar equation. This is just the homogeneous equation, right? Homogeneous system where you have on the right hand side you have a zero vector and you're just solving ax equals to 0, right? So solving the eigenvalue problem turns into solving this homogeneous system, except there's one issue. In the homogeneous system, you know what A star is. In this problem, we don't know what A star is. So because lambda, remember that lambda and x are the unknowns now, because we don't know the eigenvalues and we don't know the eigenvectors. So lambda is something that we first need to find. So the first step is to solve. So why did I erase that? Let's just keep that. So first we solve for the eigenvalues. Okay, so we're trying to solve a minus lambda I x equals 0. Okay, so let's think about this equation for a minute. This is of course a homogeneous system. We're trying to look for, these are the, if you remember, these vectors, if they're non-zero, they're in the null space, right? So x is in the null space of a minus lambda I, whatever this matrix on this is, right? So x is in the null space, right? And if x is in the null space, then if you remember, I really want these eigenvectors. We are looking for, sorry, we're looking for non-zero eigenvectors, right? The zero eigenvector isn't really special. We really want non-zero eigenvectors, which means we're looking for a non-trivial sorry, we're looking for non-trivial vectors in the null space. So when do we have non-trivial vectors in the null space? That only happens, if you remember, that only happens for singular matrices. When matrices are singular, then and only then do we have non-trivial vectors in the null space. Of course, I'm talking about n by n matrices, okay? So what do we do? If a minus lambda I, if I want a non-trivial solution to the null space problem, then a minus lambda I should be singular, which means what? Which means the following. If you have a singular matrix, another way of a matrix being singular is that the determinant of a minus lambda I is going to be 0. Okay, so this is the new equation that we need to solve. So this is now an equation for lambda. It doesn't have the eigenvector here. This equation was, again, it needs to satisfy this equation, but this equation has two unknowns. It has a lambda and an x vector. So we've just gotten rid of the x and we have a new equation, and we call this the characteristic equation. Okay, so that's important. So the characteristic equation says that the determinant of this matrix is going to be 0. So this equation, we solve it to get lambda. Okay, so I'm going to do an example with you to show how we can solve this equation. So that's the first thing that we need to learn. how to solve this. And then let's suppose, assuming that you solve this, assuming once you find all the lambdas, then you can solve a minus lambda I x is equals to 0. How can you do that? Of course, because this equation is nothing but a star x equals 0, and we know how to solve these problems. We spent a lot of time trying to solve the null space and trying to find the basis for the null space, and that's just an easy problem by elimination that we know how to tackle. Because once you know the lambdas, you know what this matrix is. So then you can solve this problem. Okay. So this is something we already know. But I'm still going to do a few examples with you just so you have an idea. Okay. So let's do as many examples as we can to really get a hang of what's going on. So let's start. Let's start with the easiest example that we can really start with. Let's start with the 2 by 2 identity matrix 1 0 0 1. And we can expect what answers we're going to get, because for example, if you think about the 2D space and if you think of all the vectors, and right, we really know that all the vectors multiplied by the identity matrix remain the same, which means every possible vector is an eigenvector, right? But let's see what we get when we try to solve ax equals lambda x, right? So I know that I need to solve a minus lambda I. X is equals to 0, which means first thing that I need to do is solve the equation determinant. I need to solve the determinant of a minus lambda I is equals to 0. Okay, so what is this a minus lambda I? So a minus lambda I is equals to, what was matrix A? It was just the identity matrix. What was negative lambda times I? It is 1 0 0 1, again the same thing. And so we have 1 0 0 1 minus lambda 0 0 lambda, and this equation just becomes 1 minus lambda 0 0 1 minus lambda. So really, doing a minus lambda I only subtracts lambda from your diagonals, and we'll see that it happens in all cases, right? It's really a simple equation. Lambda is only on the diagonals, so only the lambda gets subtracted from the diagonals. Okay, so we have a minus lambda I, but we really want the determinant of this matrix. So we want the determinant of 1 minus lambda 0 0 1 minus lambda to be equals to 0. So that's what we're going to do. Okay, so what do we do? Now this is a 2 by 2 matrix. Easy to find the determinant. We know that multiply this with this and then subtract this with this. So this is really simple. 1 minus lambda times 1 minus lambda minus 0 is equals to 0. So the equation is really 1 minus lambda squared is equals to 0, which is a quadratic equation, but easy to solve because it just tells us that lambda is equals to, so this is just, so 1 minus lambda is equals to 0 and 1 minus lambda is equals to 0, right? So two factors, two same quadratic factors, which means lambda is equals to 1 for both cases. So it's a repeated, so what we have here is a repeated eigenvalue, right? We're just getting one eigenvalue. Okay, even though it was a 2 by 2 matrix, and we'll see how many eigenvalues and eigenvectors we can get. Okay, so we have lambda. Okay, now we need the eigenvectors. How do we solve for the eigenvectors? Okay, so once you solve this equation, we need to solve this equation for x, right? So we need to find what's in the null space of a minus lambda I. So now we need to solve a minus lambda I x is equals to 0 for x. Okay. So what do we have? We have A was the identity matrix 1, 0, 0, 1, and minus what's lambda? So lambda was 1. Okay. So lambda was 1. Okay. So 0 and sorry, 1, 0, 0, 1, and x. So this is just A, and then x is equals to 0. And what do I get? This is just going to be the 0 matrix, right? So this is 0, 0, 0, 0, x is equals to 0. So really, all I really have is if this matrix is 0, then this is going to be all my eigen, all vectors, all non-zero vectors, right? So all the vectors are eigenvectors really, but really it's a bit unfair to say that these are all non-zero vectors because all these vectors can be characterized by writing them as this, right? So for example, if you have a two-dimensional space, we know that the way to write any vector, we can take basis vectors, right? So we can take I vector and j vector, and they can write down my whole space. So I can say that x is equals to something times alpha times 1, 0 plus beta times 0, 1. So I've written all these vectors using, so these are all the eigenvectors. So really, if you think about it, it's this line and it's this line, right? So we've written down the basis vectors, and these give us all the possible eigenvectors, right? Okay, but really it's just all non-zero vectors which we've written down in basis form. In basis form. Okay, so really what we're saying that we have one eigenvalue and we have two eigenvectors. We say we have two eigenvectors because, or if that's confusing, let me say we have two independent eigenvectors, right? Because that's the maximum number of independent vectors that you can have in two-dimensional space, even though it's all like even this is an eigenvector, but it's not an independent eigenvector. This vector can be written as if this is 3, 4, this vector is 3, 4. I can write this as this vector v, then I can write it as 3 times 1, 0 plus 4 times 0, 1, right? So it's 3i plus 4j. So the two independent eigenvectors are just I and j. So that's the first case. So the identity matrix has one eigenvalue and two independent eigenvectors, right? So it really, here's a simple fact that the maximum number of independent eigenvectors in Rn can be n, because that's of course the maximum number of independent vectors that you can get in Rn. So why should eigenvectors be any different? Okay. All right. So let's take another example. Let's take example number 2. Let's take a similar matrix but slightly different, right? So 0, 1, 1, 0. This is the two-dimensional permutation matrix. It's really close to the identity matrix, but if you recall, this is the same as the reflection matrix, right? So I think we did this example yesterday where we just guessed the eigenvalues, right, in the previous video. Yeah, we guessed the eigenvectors and eigenvalues, right? So this was one eigenvalue. Let's see if we can solve this using the method that we have now. Okay, so first thing that I need to do is I need to solve determinant of a minus lambda I is equals to 0. So this is going to be 0 minus lambda, 1, 1, 0 minus lambda. And I need to find the determinant, right? So the determinant of this matrix is going to be 0. Okay, so what do I have here? I have minus lambda, 1, 1 minus lambda equals to 0. What does this equation give me? This gives me minus lambda is lambda squared, minus 1 is equals to 0, lambda squared is equals to 1. I get two eigenvalues, right? I get plus and minus 1, that was expected. And then I can find the eigenvectors. So the eigenvectors are going to be 0, 1, 1, 0. So for the eigenvectors, remember we have to solve a minus lambda I times x is equals to 0. So I need to solve this equation for x. So first we do it for lambda equals to 1. What do we get? So we have 0. So this was a minus lambda, right? So I can write this as minus 1, 1, 1, minus 1. This is nothing but a minus lambda I. Okay. And now I want to solve it for x, right? So being multiplied by x1, x2 is equals to 0. So I'm looking for the null space. Okay, and so we can just solve this equation, right? Let's solve it by elimination. How do we solve it by elimination? We have minus 1, 1, 1, minus 1, and we can, if you want, we can augment the 0, 0 vector here, but that won't change anything, right? Okay, let's do elimination. We have, we can do simply R2 plus R1, or rather R2 minus 1 times R1, right? So that will just add the two rows together. I have minus 1, 1, 0, 0, and then I can just do, so this was 1 plus minus 1 was 0, 1 plus 1 gave me 0. So, okay, what does this tell me? This tells me the following. This is the first equation, this is the second equation, it's just telling me 0 equals 0. And this equation is telling me that I can write this as minus x1 plus x2 is equals to 0. And this equation is telling me 0 equals to 0. So I know that this is a consistent system. I will get some solution. And we can solve this equation. So minus x1 plus x2 just gives me x1 is equals to x2. So what is the solution going to look like? X is equals to x1, x2. And what I'm really getting is both of these terms are equal. So if the first value is alpha, the second value is also alpha. So it's really alpha times 1, 1. Right? So we just take out the common factor and you get the eigenvector. And this is the first eigenvector. This is, to say that this is one eigenvector is a bit unfair because it's a whole line of eigenvectors, but we're just interested in the basis, right? So this is the first eigenvector. So we have 1, 1, and that was exactly, I believe, what we got yesterday when we were playing around with the matrix, right? So this was the matrix and 1, 1, and 1, right? So we tried it out and we did get eigenvalue 1 and the corresponding eigenvector 1, 1, right? Okay. It's not, you can even say that 2, 2 is the eigenvector, right? Is the eigenvector. It's not, technically it's not wrong because it also remains unchanged, right? But we take out the common factor so we know we deal with the simplest possible vector, right? And that's perfectly fine. Okay, so in one line you're just going to deal with one. Okay, let's do it for lambda equals minus 1. We got two eigenvalues, 1 and minus 1. Let's do it for lambda equals minus 1. So first let's do, so a minus lambda I, which is 0, 1, 1, 0, minus, and lambda was minus 1, so this just becomes plus 1. And we get a minus lambda I is simply 1, 1, 1, 1. Okay, so that's the equation that we need to solve. And a minus lambda I, so we need to solve x1, x2, and then 0, 0. Okay, so let's do elimination. You don't really need to do elimination here. It's extremely easy to see because they're both the same equation, but if you want, we can do this. This is just the same equation, right? This equation is saying x1 plus x2 equals 0. This is also saying x1 plus x2 equals to 0. Okay, sorry for that interruption. I had a network issue. So I was saying that these are really the same equation. You can eliminate the entire second row and it will give you 0, 0, 0. You can do R2 plus R2 minus R1 and you just get 0, right? So the equation really is x1 plus x2 equals to 0. And what does that tell us? That tells us that x1 is negative times x2, right? So if we write the solution down, then that's the first entry is x1, second entry x2 is equals to first entry same negative times x2, right? So minus x2, x2. So we can really take this, whatever x2 is, let's call it alpha, right? So alpha, and we get negative 1 and let's just keep it x2. So negative 1 and 1. So here's my other eigenvector. So in this case, what we got two eigenvalues, lambda equals to 1 and lambda equals to minus 1, and two eigenvectors, right, or two independent eigenvectors, which were lambda equals, sorry, not lambda, which were 1, 1 and minus 1, 1. Okay, right. So far easy examples, nothing really happening, but we're just getting a flavor of this. This equation is really what boils down to, right? We get a quadratic equation. So far these equations were simple. Let's try maybe a case where these are not as straightforward. So let's see, let's take another example where we might get something different. So let's try example 3. Let's do 2, 0. This is a simple example, maybe. I don't need to do this. This is still a simple example, so let's try to do this quickly. If you try to solve this, actually I won't solve it completely, you can solve it on your own. You'll see that the lambda is just going to be equals to 2 in this case, and the eigenvectors are going to be, so you'll get one repeated eigenvalue, and the eigenvectors are going to be the same as the previous case in what we got in the identity case, which were 1, 0 and 0, 1. You can try this out on your own. Simple case. I'm going to try 2, 1, 1, 2, right? Okay, so this is A. So I want to do determinant of A minus lambda I is equals to 0. So let's solve that, which is 2 minus lambda, 1, 1, 2 minus lambda is equals to 0. So that's the determinant. So how do we compute the determinant? It's going to be 2 minus lambda times 2 minus lambda minus 1 is equals to 0. So that's the first equation that's going to give us at least a long quadratic equation. So this is, let's try to write this out. What do we get? We get 4 minus 4 lambda plus lambda squared minus 1, right? That's what we get. And so the equation is going to be really lambda squared minus 4 lambda and plus 3. Okay, so this is a quadratic equation. So this is my characteristic equation. This is the first time I've gotten at least some kind of longer quadratic equation with all three terms. So let's see, how do we solve this? So first thing to notice is, of course, that this is a quadratic equation, and you can factorize it, or maybe you can apply the quadratic formula, whatever technique that you think. If this can be factorized, and it probably can be factorized, let's try it out. So I believe if we do lambda squared minus 3 lambda minus lambda plus 3, then that would be a right way to break this down. So I get factors lambda minus 3 and I believe lambda minus 1, right? I believe that's the correct factorization. So I get 2 eigenvalues, which were lambda equals to 3 and lambda equals 1. Okay. All right. So what we really need to do now is, once we have the eigenvalues, let's find the eigenvectors. Okay, so let's try lambda equals to 3 first. My a minus lambda I x equation is going to be the following. So a was 2, 1, 1, 2. So I have 2 minus 3, 1, 1, 2 minus 3. That's my a. And x is going to be just x1, x2 is equals to 0, 0, right? So the equation is, I have minus 1, 1, 1, minus 1, and I have x1, x2 is equals to 0, 0. So we can do elimination here, and let's augment it. Minus 1, 1, 0, 1, minus 1, 0. Let's see what we get. Okay, should be simple. The entries are just ones and minus 1. So let's try R2 minus 1 R1, which is just R2 plus R1, right? So I get minus 1, 1, 0. So 1 plus 1 is 1, plus minus 1 is 0, minus 1 plus 1 is 0. And so the second equation is just second equation is just 0 equals to 0. So we don't need to worry about that. This equation is saying negative x1 plus x2 is equals to 0. So this is a similar equation to what we got in the reflection matrix case, right? So I believe it was the reflection matrix, right? Yeah. So x1 is equals to x2. So the first eigenvector is really, if I write x1, x2, and if this is just the same value x1, so it's just going to be some alpha times 1, 1. Both the values are same, and we can factor out the common factor by alpha, right? So this is the eigenvector. And let's just do it for lambda equals to 1 as well. Oops, I believe I've messed up the order of the pages here. That's fine. We'll just fix it up later. Okay, so let's do lambda equals 1 now. So lambda equals to 1. We need to solve a minus lambda I. X is equals to 0. So this is just the terms are 2 minus 1, 1, 1, 2 minus 1, and x1, x2 is equals to 0, 0. Again, these are simple computations, but I'm just doing as many as possible so you have an idea. So the equation in this case is going to be this augmented with 0, 0, right? And we know what the solution is. The solution to this is just x1 is equals to minus x2, and the eigenvector is going to be 1, minus 1, or you can write that as minus 1, 1, right? So this is, in this particular case, we got the same eigenvectors that we were getting in the second case that we did. So 0, 1, 1, 0, notice that we got the same eigenvectors. Sorry, not here. We got where are they? So in the case where we did, oh, sorry, I think I changed the order. Yeah. So over here, notice that we got the same eigenvectors, minus 1 and 1, and the first one was 1 and 1, right? So ignoring the wrong order. So notice case 2, examples 2 and 4 tell us something important. Example 2 was 0, 1, 1, 0, and example 4 was 2, 1, 1, 2. So this matrix is very closely related to this matrix. If this matrix is A, I can write this matrix as A plus 2 times the identity matrix, right? So it's just I've added 2 in the diagonals on this one, right? So if you do, I can even show you 0, 1, 1, 0 plus 2 times the diagonal matrix is going to be 2, 0, 0, 2. And if you add these matrices together, you get 2, 1, 1, 2, right? So that's the relationship. And what did we find in the eigenvalues? So the eigenvalues of this first case were, so here are the eigenvalues. Yeah, so the eigenvalues were just +1 and -1 in this case. So the eigenvalues for this one were +-1, and the eigenvalues for this one were what? They were 3 and 1. So if I write them as alpha equals to 1, sorry, lambda equals to 1 and lambda equals to -1, over here we had lambda equals to 3 and lambda equals to 1, which is, if you see the relationship, what's really happened is 2 has been added to both the eigenvalues, okay? And the eigenvectors remain the same. The eigenvectors for this one are 1, 1, -1, 1. And for this one, were also 1, 1, and -1, 1. So what can we conclude? We can conclude the following, and I can even show you that if AX is equals to lambda x, that A has eigenvalues lambda and eigenvectors x, then we can say, okay, AX plus identity times x on this side, or rather plus, what can we do? Let's say plus alpha times identity x is equals to lambda x plus identity plus alpha identity x, right? So what we're doing is we're just adding two sort of, we're just adding a scalar times the identity to the original matrix, right? So for example, A plus 2i, that was the case here. So what do we get on the left hand side? We get, if we're doing A plus alpha I times x, and on the right hand side we get lambda plus alpha x, and we can do this because the identity really doesn't change anything. Okay, so what can we conclude? That if A has eigenvalues lambda, then A plus alpha I will have eigenvalues lambda plus alpha, right? And we can only do this because x, we know every vector is an eigenvector of I. That's the reason we can do this, because if this x was different, for example, we cannot say ax plus bx is equals to lambda x plus alpha x. That is, we don't know that if we're saying ax is equals to lambda x and bx is equals to alpha x, this really is a problem because we don't know if they have the same eigenvector, right? Maybe A has eigenvector 1, 1 and B doesn't have that eigenvector. So this is wrong. So I can't do this for any A plus B. I can't say A plus B x is equals to lambda plus alpha x. This whole thing is incorrect, right? Because x may or may not be, A and B may or may not share the same eigenvector. But in this case, we can do this because the identity matrix has every vector as an eigenvector. So that's a nice case. Okay. All right. Let's do a slightly different example. I'm just going to do as many examples as I can today so we get a good hang of these computations. Okay, let's try another similar sort of a matrix. So let's try. I'm still sticking to the 2 by 2 case. I'll move to a 3 by 3 case in a bit. I'm not going to ignore them. So number 5, let's do an upper triangular matrix this time, right? So let's say we do 2, 3, 1, 0. Okay, let's see. Matrix A. And I've chosen this to be an upper triangular matrix because we'll see something important. So let's see A minus, let's call it U. So we know that it's an upper triangular matrix. With U, I want to solve again the determinant U characteristic equation U minus lambda I is equal to 0. So how do we do that? The way we do that is 2 minus lambda, 1, 0, 3 minus lambda is equals to. So I want to find the determinant of this, right? The determinant of this is equal to 0. Okay, how do we find the determinant? Multiply these two entries and this is going to be nothing. So 2 minus lambda, 3 minus lambda is equals to 0, and this is already a quadratic equation which has been factorized. So I can immediately say if this is equals, if the product of these two is 0, then lambda equals to 2 or lambda equals to 3. These are the two eigenvalues. And this was really convenient because I didn't even need to do this. For an upper triangular case, you can just read off the eigenvalues on the diagonal. They're just staying right there. They just need to see what they are. Okay, so what about the eigenvectors? We do need to solve for the eigenvectors, right? Let's see what we get. So lambda equals to 2. I need to solve a minus lambda I x. So a minus 2ix is equals to 0. How do I do that? Well, the way to do that is, what is this matrix? So 2 minus 2 is 0, 1, 0, and 3 minus 2 is going to be 1. Okay, so x1, x2, let's augment this with the right-hand side, which is 0, 0, and let's try to see what these equations are. This equation is telling me x2 is equals to 0. This equation is telling me the same thing, x2 equals to 0, which means my solution is x1. Sorry, my solution is, if I have x as x1 and x2, then the solution is really x1, 0. x1 is free, right? No pivot variable here, but x2 is 0. So I can just write this as x1 times 1, 0. So this is my eigenvector. And what about the second one? Let's try to do the second case. So lambda equals to 3, I believe. Yeah. Okay, so lambda equals to 3, we get 2 minus 3 is minus 1, 1, 0, 3 minus 3 is 0, x1, x2, and is equals to 0, 0. So what is the equation in this case? Minus 1, 1, 0, 0, augmented, 0, 0. And it's just, this equation is 0 equals to 0. Ignore that. This equation is saying minus x1 plus x2 is equals to 0, which means x1 is equals to x2. So this has two eigenvectors, which are so x1, x is equals to alpha times 1, 1. That is, they're both the same entry, right? Alpha, alpha, x1, x1, x2, x2. Okay, so this is the second eigenvector. So in this case, we got two eigenvalues and two eigenvectors. Okay. Let's try an example. We've gotten a hang of how do we do 2 by 2 examples. Maybe we can try to see one more example where we get a problem, right? So let's try to do a case where we might not get a nice solution. Okay, so let's try to do this case. Which example is this? I've done 5 examples. Okay, let's try to do 6. So let's do matrix A equals to 1, 2, or 1, 3, and let's make this 2 and 6. Okay. So what I've really tried to do is try to make this matrix singular, and let's see what happens. Okay, so let's try to do A minus lambda I equals to 0. Try to find the determinant. So going to be 1 minus lambda, 3, 2, 6 minus lambda is equals to 0. Okay, so what's the equation? The equation is 1 minus lambda, 6 minus lambda, minus 3 to the 6 equals to 0. Let's try to expand this term on the left hand side, which is 6 minus 6, sorry, so 6 minus, let's try to do this, 6 minus, hopefully I don't make any mistakes, minus minus plus lambda squared minus 6 equals to 0. So these two cancelled out and I get lambda squared minus 7 lambda. Oops. Have I done that correctly? I believe so. So lambda squared minus 7 lambda is equals to 0. Okay, so let's take lambda common here. Lambda minus 7 is equals to 0. So I get two values, lambda equals to 0 and lambda equals to 7. Why did I get lambda equals to 0? I got lambda equals to 0 as my eigenvalue because this is a singular matrix. The reason I know immediately that this is a singular matrix, notice the rows. This row is twice the first row, or notice the columns. The second column is 3 times the first column. So it was bound to happen this way, and I did this in the example that we did in this first lecture, that if you have a singular matrix, lambda equals to 0 is going to show up, and this doesn't really have an eigenvector associated with it, right? Because this is telling me we have a non-trivial null space of A. Okay, but what about this lambda equals to 7? Surely we must be able to find an eigenvector associated with that, right? So let's do that. Let's say, actually, let's try to see what happens. So if I try to do lambda equals to 0, what will I really be solving? So if I do A minus lambda x is equals to 0, A minus lambda I x is equals to 0, the eigenvector, since lambda is 0, you're just solving Ax equals to 0, which means your eigenvector that you were solving, the eigenvector is going to be equal to the vector in the null space, right? The line that disappeared over here is actually the line that is in the null space, right? So when you try to solve it for lambda equals to 0, you're just trying to solve the equation of the null space, and you can do that, right? So that's just 1, 3, 2, 6, and if we try to find the null space for this one, let's try to do that. It's just 1, 3. We can eliminate the second row completely. I know I can do this if I just do R2 minus 2 times R1. So what is this equation telling me? X1 plus 3x2 is equals to 0, which means x1 is equals to minus x2, which means the eigenvector is really minus 3x2 and x2. So this is the eigenvector, right? I wrote it as x1, x2. This is the first entry. Second entry, which means I can really write it as alpha, so, or x2, take that common, minus 3, 1. This is my eigenvector associated with lambda equals to 0, right? So you do have that eigenvector, right? But that eigenvector is actually sort of trivial in that it shrunk down. This, if I show you what happened. So let's say this was the original vector, which was minus 3, 1, right? So minus 3, 1, this was the vector. And when you apply A to this, so if I apply A on this space, what happens is this matrix, this vector shrinks down. This scales down, this entire line actually scales down to 0, becomes 0, right? And the rest of the space, well, we'll see what happens to the rest of the space. I really recommend that you watch videos from 3 Blue 1 Brown channel, which contain really nice animations of what's really going on. Okay, but let's not waste any time. Let's just solve it for lambda equals 7. So what do we get? We have 1 minus 7 and 6 minus 7. So 1 minus 7 and 3, 2, and we have 6 minus 7. And let's try to solve it for the null space. Okay, so here we go. We have minus 6 here, 3, 2, minus 1 here, 0, 0. What do we do? Okay, so R2 plus, or what do we have? So I can do R2 plus 3 times R1, or minus 3 times R1. And that will give me the first row as it is, minus 3, 3, minus 6, 3, 0, and this is going to be 0, but over here I have 2 plus 3 times, actually I should really be doing R2 plus 1 upon 3 times R1, right? So I need to divide this by 3, which will make it 2, and then I can add this to make it 0. So this becomes 0, and then this entry is minus 1 plus 1 upon 3 times 3, right? These to cancel out, minus 1 plus 1 is 0. So again, nice little equation, turns out to 0. What is this equation telling me? It's telling me minus 6x1 plus 3x2 is equals to 0. The solution to which is minus 6, well, 6x1 is equals to 6x1 is 3x2, which means x1 is just, you can say, or you can say x2. Let's say 3x2 is 6x1. So x2 is really 2 times x1. So if I write the solution as x1 and x2, it's going to be alpha here and 2 times alpha here, right? Whatever you write here, it's the second entry is going to be 2 times that entry. So the eigenvector, if I take the alpha as common, is 1, 2. So this is my eigenvector. So I have, in this case, I got 2 eigenvalues, lambda equals to 0, lambda equals to 7 distinct eigenvalues. And what did I get? I got eigenvector associated with this one was minus 3, 1, I believe, and with this one was 1, 2. So even if you have a singular matrix, the lesson to take away from this example is even singular matrices can have two distinct, or can have n distinct eigenvalues, and n independent eigenvector, right? So it being singular has no bearing on what the eigenvalues and eigenvectors are. Of course, this is a special eigenvector which shrinks down to 0, but it's still there, right? So it has an eigenvector. Okay, so this was a good example to do. Okay, let's do one more example. Yeah, and then we'll end the lecture. So let's finally do a 3 by 3 case. Let's try to make an example which might be slightly easier or solvable. Let's say, okay, let's put 1, 2, 3 in the diagonal, and let's put 2, 1. So let's put 0, 0 here, 2, 3, and 1, 1 here. Okay, I'm going to demonstrate 2 things in this example, right? Hopefully I've made a, yeah. Okay, if you've noticed this example, the first row is a scalar multiple of the third row, so they're not independent, so it's a case similar to the previous case in which we had a singular matrix. And another important thing is that now we need to find the determinant of a 3 by 3 case, which we haven't really done so far. So we did that in the last class when I showed you how to do that, but let's try to do this in this case. Okay, a minus lambda I equals to 0. So what's this going to be? 1 minus lambda, 0, 1, 2 minus lambda, 2, 1, sorry. Oops, this is 2 minus lambda, and then 3, 0, 3 minus lambda. Okay. All right. One thing that you can do, you can find the determinant. I showed you the formula was that you go along a row and then you multiply it with the cofactors, right? So one thing that you can do is you go across this row, make the checkerboard, right? So plus, minus, plus, minus, plus, minus, plus, minus, plus, right? So the first case could be 1 minus lambda times its cofactor, right? So we can write this as the determinant of this a minus lambda I can be written as 1. So let's write this as a11 times its cofactor minus a21 times its cofactor plus a31 times its cofactor. So I'm going down this row, this column. So what do we have? We have 1 minus lambda, and the cofactor for this one is simply remove this row. If you remember this, remove this row, remove this column. This is the matrix that we get. Okay, so let's just write that here. So it's 2 minus the determinant of 2 minus lambda, 1, 0, 3 minus lambda. And then second equation is going to be minus a21 was 2, and then the cofactor for this one is going to be, what are we going to do? We're going to ignore this. So this was the entry, right? So we're going to ignore this row and ignore this column. So the matrix we get is formed by these two blocks, right? So I can write that down here. And that's going to be the determinant of 0, 1, 0, 3 minus lambda. And you can see that it's already getting a little complicated, but we have some nice entries, zeros here, so that might simplify my example. And then finally plus 3, and I'm just going to write that down. That is going to be 3. Remove the first column, remove the third row, and I get 0, 1, 2 minus lambda, 1. Okay, so these are now just 2 by 2 determinants which we can compute. So let's try to do them. 1 minus lambda. Over here I have 2 minus lambda and 3 minus lambda. The other one is just 0. This one is 0 times 0, nothing there. What about this one? This one has 0 times 1, so this has plus 3 times 0 times 1, that's fine, minus 1 times 2 minus lambda. So we change the sign, minus, and I have 2 minus lambda here. Okay, so what does this give me? This is the determinant. This whole expression is now the determinant of this one. Okay, and this is going to give you a cubic equation. If you solve this, maybe you can see that this is a common factor here, 2 minus lambda. So you can write this as 2 minus lambda times, and then you have 1 minus lambda, 3 minus lambda, and then you have minus 3 equals to 0. So this can be easily solved. You have 2 minus lambda equals to 0. That's the first equation. So one of the eigenvalues is 2. And then you can solve this quadratic equation, 1 minus lambda, 3 minus lambda, minus 3 equals to 0. Let's try to do this one. So what do we have? Let's try to solve this. 3 minus lambda minus 3 lambda plus lambda squared minus 3 equals 0. Lambda squared minus 4 lambda is equals to 0. And then we have lambda minus 4 equals to 0. So we did get a 0 eigenvalue because it was a singular matrix, and lambda equals to 4. So we have our 3 eigenvalues. It was, if we had expanded this, we would have gotten a cubic equation and we would have been slightly in trouble, but because there was a common factor here, I think you should make use of whenever you can factorize this. If it's already in a nice form, just make use of it and convert it into one linear equation and one quadratic equation. Okay, so this is basic algebra that you should be familiar with. So you have 3 eigenvalues, and now you can find 3 eigenvectors corresponding to lambda equals 2, lambda equals 0, lambda equals to 4 by solving these 3 equations. So first you need to solve a minus 2i equals to x equals 0. So you need to x is equals to 0. So you need to find the null space of this. For lambda equals to 0, it's just ax equals to 0 that you have to solve, and a minus 4i x is equal to 0. So you have to solve these three. Solve for their null space. And that's it. That's how you find the eigenvalues and eigenvectors even in a 3 by 3 case. What's important here is that you should know how to compute the determinant of a 3 by 3 case. And that's where the difficulty lies. One thing that we could have done, by the way, I'm just going to show you a nice little trick that can simplify your computation of the determinant. So what you can do is, I said that you can go across any row, right? Any row or any column. So I could have gone across this column as well. And this column is nicer to go across because two of the entries are already 0. So I can also say that the determinant is going to be, this is A12, A22, and A32. So A12 with its cofactor plus A22 with its cofactor plus A32 with its cofactor, right? And the signs are negative, positive, negative. So I can change these signs, negative, positive, and negative. Okay. So, but A12 and A32 are already 0. So I don't need to write this. I don't need to write this. The only thing that I need to write is A22 times its cofactor. So 2 minus lambda, then the determinant. So what determinant will I get if I remove this row and this column? So this entry, this entry, this entry, and this entry. So that's the matrix I need to construct. So the determinant of 1 minus lambda, 1, 3, and 3 minus lambda. And you can see that you get the exact same equation that you got. This equation is 2 minus lambda, and the determinant on the inside is 1 minus lambda, 3 minus lambda, minus 3. That's exactly what we got